All right, so this is the last video I'm going to make for 6.3. We might go over some examples in class later. But in this video, I want to talk a little bit more about combinations. There's an alternate notation for CNR, like the number of R combinations selected from N objects. You could write it like this, where you have parentheses and you put N on top and R on the bottom. And you usually read this as N choose R. I mean, if you write NCR, that can be read as N choose R as well. All of these could be read as N choose R. Because a nice way to think about this is as the number of different ways of choosing R objects from a set of N objects, right? Like in the previous example, we had like a club of 30 people, and we wanted to count the number of ways of just choosing 4 of them to make a committee, right? And how many different ways can you do that? Where the order of the numbers, the elements you're choosing doesn't matter. So there's a relationship to this thing called the Binomial Theorem and the coefficients that show up in the Binomial Theorem. So I want to explain that relationship in this video, and also the relationship to something called Pascal's Triangle, which is related to both Binomial Theorem and also N choose R combinations in counting. So the Binomial Theorem says that when you take a plus b to the power n, you get this. It's like if you expand the power of of a binomial like that, you end up getting this sum, which says you're going to do n choose k and have k go from 0 all the way up to n, and then you could do like a to the power k and b to the power n minus k. Something like that. And this is n choose k right here. These are the binomial coefficients. Okay, and the numbers you get from that, as those coefficients are the same numbers you get when you count the number of ways of selecting, of choosing R things from N things. Or in this case, I guess I called it k. So I want to explain why that is. Let's look at the example of a plus b to the power 4. This is going to be a plus b times a plus b times a plus b times a plus b. And when we multiply that out, we're going to get a to the power 4. How many copies of a to the power 4 are we going to get? Well, there's only one way of choosing a from every one of these binomials, right? You got to pick a from this one and pick a from that one and pick a from that one and pick a from that one. So that's a 1. For the next one, we're going to have a cubed times b. And so we're gonna take of these 4 different copies of the binomial, we're going to choose 3 of them to be the a, and we're going to choose one of them to be the b, right? And how many of those are there? Well, we could do a, that's one way. We could do a, that's a second. Or we could do a, that's a third. Or we could do b, that's a fourth. So we have 4 of those total. So we can think of this as that is the number of ways of taking the 4 different binomial copies here, the 4 factors, and the number of different ways to choose one of them to be the one from which we select the b. It could have been the b comes from the last one, or the second to last one, or the second one, or the first one. There's different, we could choose the b from one of them. And the other 3 are going to be a's. All right, this one over here, this is saying, what if we're not selecting any b's? They're all going to be an a, so of the four binomials, select none of them to be b. 4 choose 0 is always 1. Anything choose 0 is always going to be 1. And then the next number here is going to be, what if we're going to have 2 a's and 2 b's? So a squared times b squared. So now we want to say, let's take the 4 different binomials and choose 2 of them to be where we pull the b's from. And the other 2 are by default going to be the a's. 4 choose 2, that ends up being 6. Like that. That's 6. And then for the last one, sorry, there's 2 more. Then we'll do a times b cubed. And so for this one, we're going to say, let's take the 4 options and choose 3 of them to take the b from, and then the 1 remaining will be the a. So 4 choose 3, that also equals 4. And then we'll say, finally, we're just going to take 4 and choose all 4 of them, right? All B's and no A's at all. So it's just going to be B to the power 4. And that, when you do 4 choose 4, it's like you take all of them. So there's only one way to do that. There's only one way to pick all 4 things. And that's a 1. N choose N is always going to be equal to 1. So I hope this kind of describes, and I hope this kind of shows you the connection between this binomial theorem and the idea of choosing, right? This is a combinatorial process. It's a counting process of in how many different ways can I choose A's and B's from these 4 different copies of the binomial, so that I produce all these different terms that I get by expanding it. So there's that. Now the last thing I want to show you is Pascal's triangle. Pascal's triangle is kind of like a shortcut for finding all of these numbers. If I start with a 1 and then 2 1s beneath it, what I can do is create the next row of the triangle. I'm going to make an infinite triangle that extends downward, and I get each row by adding together the 2 numbers that are sort of diagonally above. So 1 on the left, and then 1 plus 1 is going to be 2, and then I have a 1 on the right. Oh, you're always going to have 1s down the left and right sides. But then my next row is going to be 1, and then 1 plus 2 is 3, and 2 plus 1 is also 3, and then I end with a 1. My next row is going to be 1, and then 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then I have 1, 1 plus 0. You could think of there being zeros outside of this triangle. So 1 plus 0 is 1. And then I'll have 1, 5, 10, 10, 5, 1, and so on. I'll put a dot, dot, dot down here. So this is Pascal's triangle. It goes down forever. And the entries in the triangle are actually the values of n choose r. So if we divide this into rows like this, each one of these rows corresponds to a value of n. We have n equals 0 as our top row, n equals 1, n equals 2, 3, 4, and 5. So there's the values of n. And then if we go the other direction, let me grab my other pen. Where's my other pen? There we go. If we go the other direction, like this, these like sort of columns correspond to the values of r. So this is r equals 0, r equals 1, r equals 2. This will be r equals 3, r equals 4, and r equals 5. And so on. This will go on forever, and this will go on forever. Okay. And so then, looking through here, if you want to look at this, like if you want to look at one of these here, one of these numbers, this is the 5th row, 2nd column. So this right here is the value of 5 choose 2. It's always n choose r, 5 choose 2 is going to be 10. Looking through here, I can see 4 choose 3. 4 choose 3 is going to be 4. 2 choose 1 is 2. 5 choose 4 is 5, and so on. And so if you expand this out, you can figure out the value of n choose r by doing that. And they're all in Pascal's triangle, and they have this nice relationship that sort of builds on itself. It's a nice sort of recursive definition. But that's not, this is not how you have to do. Also, I think I spelled Pascal wrong. I apologize to Pascal. I think that might be a C. This is not how you have to do it, because sometimes for some problems you're going to need to do like 100 choose 25 or whatever. So you don't want to have to build 100 rows of Pascal's triangle. Instead, if you have a TI, you can go into your math and go over here to probability. These, I haven't mentioned it, but counting is applied when you study probability. So these operations are often associated with probability. You've got NCR right there. There's NPR for permutations and NCR for combinations. So if I wanted to do 5 choose 2, I could put 5C2. I could enter the 5 and the 2 in, hit enter, and I get the number 10, which is the correct answer. So that's how you can use that. You can also use the Google search bar. If you just type into Google search bar 5 choose 2, it will tell you that equals 10. Because Google is really good at math. So that's it.